radial Toeplitz operator. So please, Moisés.
Okay, got it. Well, good afternoon. It's a pleasure for me to be with you again. And let's talk about this radial operators on the polyanalytic weighted Bergman spaces. Toeplitz, radial Toeplitz operators. This is a joint work with Dr. Egor Maximenko and Dr. Gerardo Ramos Vasquez. And we talk about polyanalytic Bergman spaces. We begin with a function that we will call polyanalytic function, a function f defined on the disk, if will be called n analytic if satisfy this equation. You have this notation, and there will be n analytic functions, so that we have this presentation for f. And we have here an idea that I explained the last session. We just tried to solve by an argument of by steps. We try to solve the equation. We see that if f is k plus 1 analytic, so its derivative with respect to z bar is k analytic. So there exists k functions, analytic function, that we can have this presentation for this derivative of f. And making these operations, we know that this function is now analytic. And now we have this presentation for f. If we define f sub 0, and we can see that we could find k functions that we now could present f with this polynomial in z bar with with analytic coefficients, functions that are coefficients. And for unicity,
did you check this proof in the bulk book?
Yes, in bulk. Yes, it is in bulk, in the book of bulk. And he of course doesn't say everything, but he explains the idea very carefully, and I just try to follow his idea here.
Okay.
We have some examples of functions that live here in these spaces. The monomial function, the function 1 minus z bar. This an example. This is too analytic, but we want to have everything of the polyanalytic of the analytic functions, because it has a minimum on its boundary with a maximum in 0. And the unicity principle doesn't verify, doesn't hold, because this function is 0 on the boundary of the disk, but it is not a function 0. So now let's fix alpha and consider the usual radial weight. And for short notation, we just will use this polyanalytic Bergman spaces, are the polyanalytic function that are square integrable function with respect to this measure. And this talk alpha will be fixed, and we will often suppress the dependence of alpha. Of course, this space, the polianalítico Bergman spaces, is a reproducing kernel Hilbert space. Now we need this Jacobi polynomial for the unit interval. We call them shifted Jacobi polynomials in terms of
Moisés, just one observation. If you will follow your previous talk, you will never end. Maybe you can somehow bypass what you said last time. You just pass to the what are you going to present today?
Okay. Okay, so last time we just talked about how to construct the base, how some researchers construct the kernel. We talk about the monomial functions. We also present the basis, because as you can see, the monomials in L2, they are not orthogonal, but now the basis that we present in terms of the Jacobi polynomials, because of the orthogonality, they are orthogonal, and they are orthogonal also in frequency. So we have an orthonormal basis. Last time, of course, we talked about how could we see these polyanalytic spaces, Bergman spaces, as these infinite columns of this infinite table. The pure polyanalytic or true and analytic Bergman spaces. We talk about that these are dense. These are dense because these are polynomials in Z bar. They are dense in the continuous functions, and the continuous functions are dense in L2. So this table generates all L2. We talk about also the polyanalytic weighted Bergman spaces as these direct spaces of frequencies. We also talk about the radial operators in the polyanalytic Bergman spaces. We also talk about the diagonalization of the radial operator, the set of operators diagonalized by a family of subspaces. We gave this condition. We have a Hilbert space. Just two conditions are satisfied for the set of sets that diagonalize the Hilbert space. We just give two conditions that this space W that this space is subspace, proper subspace, eigenspace, and that there exists a rotation or there exists an operator that can separate, can distinguish these two sets, two spaces. We talk about the rotations. We say that we could see that radial operators in polyanalytic Bergman spaces are those that commute with rotations. And we talk this the commutant of the radial operators are the commutant of the rotations. And we give the structure of the radial operator in general. We could we could see them as sequence of matrices, as you can see here in this diagonal -2. We can have this matrix, this number. In the following diagonal, we can have another matrix. In the diagonal zero diagonal, we can construct the next matrix, and the next, and the next, and so we can see, we can have a radial operator seen as this sequence of matrices. And we define the algebra of the sequence, the bounded sequences, and we gave an example. We define the Toeplitz operator on the polyanalytic Bergman spaces. Is just the projection of the product. We also gave this, well, we talk about these Jacobi functions that we will need later. We could see, how can we say that? Yes, that we just, the sequence of matrices corresponding to the radial operator, the Toeplitz radial operator. We can see that sequence as the sequence of matrices for n equal 2, and we can have an explicit way to calculate the entries of every one of these matrix. We have this in terms of the Jacobi functions or in terms of Jacobi polynomials. We have these results in this paper with Dr. Maximenko and Dr. Ramos Vasquez. And we just want to know that what does this you know, the sister algebra generated by these gammas that is equal to this Ln, the set of functions that have limit, that in the limit they are this how do you say,
Scalar multiple of identity.
Thank you. I'm so nervous. Also, we have this proposition. We can see that it is not difficult to prove that this algebra is subset of Ln, because if the radial function has limit in the boundary, we know that we prove that the limit of these gammas are this non-zero multiple of the identity. And of course, we have as a corollary that this is upset, because in the last proposition, oh, here, well, in the last proposition, we know that we have this contention because here, Professor Vasilevsky proved that proved this result in the case, in the analytic case, but in the polyanalytic case, we have a very more complicated expression that uses this Jacobi functions, and of course, by this proposition, we know this that G sub n is subset of Ln, but because Ln is a sister algebra, the result follows. Now I just want to give an example. Let's suppose that we have this indicator function and that the entries, as we can see by the last formula, we can they can be calculated, but this integral, we get the entries, the components of the matrix, where and for the two polyanalytic Bergman spaces, we can see that we have here the frequency, the -1 frequency, 0 minus 1 is -1, and so we have this matrix. The gamma is just a number. In the zero, in the diagonal, in the zero diagonal, we have this. Well, as you can see, we will have this sequence of square matrices corresponding to different frequencies, and the entries of this matrix will be given by this expression here. And as we can see, if R tend to 1, I mean, if R tend to the boundary, the entry 0, 1 and 1, 0 entry, they will be 0. Here we will have epsilon 2 square minus just epsilon 1, and this will be 1. And in the limit, we will just have the identity. That's just an example of the way to see that. Now we have this following proposition. We have the algebra generated by this sequence of matrices with a fixed frequency. We just have we just consider this function, this radial function, as the Jacobi polynomial with degree p degree, and by the orthogonality, we have that the sum of the entries is well, not the entries, the sum of how do you say, of the anti-diagonal is less to p, it will be 0. If J plus K is equal to P will be different to 0. Okay, because and by the orthogonality here we can see that will be or 0 or not equal to 0. We have this case for n equal 4. We take P equal 3, 4, 5, or 6. And we have this anti-diagonal structure of the gammas associated to radial functions. Here, this bullet means that it is numbers.
Non-zero element.
Non-zero element, and these stars are just an arbitrary entry of the matrix. And the C-star algebra generated by these gammas are Mn. We just want to give an example. We just give this definition of the basic matrices of the space of the square matrices, and let G0, E1, and V2 are elementary of the following form. These are just arbitrary elements, but we are interested that here in the last row of each matrix, we have this element different from 0, and we want to get to 0, e to 1, e to 2, but we want to give them in terms of G. Here, now we want to give by, we want to denote GP, J key, the entry J T, JK of the matrix P. The components, the entry of the component of the matrix CP. So as you can see here, G2 is non-zero multiple of I3. We solve this equation for E22 and we get this basic function in terms of G2. And because E22 is idempotent, we also could multiply E22 by itself and get this number. Now we have E22 as a product of the generators T2, of the generator D2 squared. Now let's consider the product E22 times G1. As you can see, just we will have this last row because every other element, because we're multiplying by this basic matrix by E22 in the left. Every element will be 0, but the last row will remain the same. So we'll have this expression, the entry 2, 1 of the matrix 1, the entry 2, 2 of the matrix G1. So we can decompose this product. We could decompose this product for this in terms of the basic matrix. We solve this equation for E21 and we get this expression. Now we want to substitute E22 here and we will get that also E21 is in terms of linear combination of products of G's. We have these explicit formulas for the coefficients. Now, finally, we consider these products. We also decompose this product by the basic matrices. We solve this equation for the E20. And now we will have e22, e22, we substitute e22, and we also substitute the value of e21. Now we also will have the matrix e20 as a linear combination of products of these matrices. So we have this general result where we say that the basic matrices can be written as in terms of the generators. You can see that this last example is just the way to how you prove this lemma. But in general, we want to know that the algebra, D-star algebra, if this C-star algebra generated by D0, Gn minus 1 generate all the algebra Mn. And this is true because by the last lemma, we get e22, e21, and e20. But because A is closed under the operation involution, we get e22, e12, e02. But because A is an algebra is closed under the product, so we can also have this EPQ. And finally, the linear combination of the matrices will generate all the space, all the algebra Mn. Why we need this this proposition? Because this result will be very useful for the separation of the states. That is the goal, the objective of the work, of this joint work. So what do we have? What do we want? We really want to know if the pure states of Ln could be separated by the generators of this algebra. We want to see that the generators of the algebra separate. If they separate, we want to know if they separate the pure states of Ln of this space.
Moisés, probably here you need to say that the idea of what you are going to do right now.
Yes, it's just the idea.
To use non-commutative analog of the Stone-Weierstrass theory. Two algebras are coincide if one algebra separates all pure states.
Yes, this is the result of Kaplansky.
This is the result of Kaplansky. And this will help you to prove what do you want to prove.
Yes, the result will help us to prove that objective. And so the pure states of the pure states here in our case are just this matrix. I think it is a general result that the pure states are given by this formula in the algebra of the square matrices. And well, we know the matrix associated to this radial Toeplitz operator, and we can see that we get this in terms of the Jacobi functions, and we define this sigma infinite as the limit of this function. Well, we could see that, we can see that sigma c separates sigma infinite. We just need, oh, yes, we need just to find a sequence of matrices such that these pure states could be separated. The idea is that we consider this function, this indicator function. We know we construct this sequence associated, the sequence of this radial Toeplitz operator associated, and as the limit of this function is 0, and we know that we know that the limit of all the sequence with this fixed frequency will be 0. We have that sigma infinite is the number 0. But sigma sigma he of A is not 0 because this function is positive it is positive, but maybe not in a subset of 0, 1, but its integral is always positive. So we could separate sigma infinite. We could separate from sigma c of A. That is the first observation. The second is that xn, I mean the pure states, the xn, it separates sigma c, but I mean pure states with the same frequency. It follows from the fact that these generators are this algebra. But we have a problem. We have a problem with the separation with different frequencies. This is a bad news for us because we here could not separate this pure state with these different frequencies. Why? Because we just think about this first pure state, sigma xi, and sigma eta. But if we subtract them, we have this integral. Now here we denote ft, this sum as ft, and this other sum by gt. And we see that this equality holds for every a in this set. If and only if for every t in 0, 1, they are equal. They will be equal if this condition holds, of course. But if we just consider c equal to 0 and eta equal to 2, well, we calculate this Jacobi function, j 0, 0, 0, j 1, 0, 0, j 0, 0, 2. Okay, we have these polynomials. Ft is, if we consider u and v, these normalized vectors, we make this operation with ft. We make this operation with f to dt. And what happened? If this b is b0, b1, u0, u1. If b1 is equal to 0, we have this equal to 0. this equal to 0, also this equal to 0. So we get b0 times square root of 3 times t. But b0 is 1. So here in gt, we have square root of t. And for ft, we make these operations with u0 and u1, and we get ft equal to square root of 3 times t this time, and gt equals the same. So we cannot, here is an explicit example that we could not separate this pure states here. We cannot separate this pure state with different frequencies, because here we have an example that show us that it is not possible. So what to do? Well, Dr. Maximenko, he had the idea based on some other works, maybe by Professor Sanchez Nungaray and Professor Maribel Loaiza. We could work with this linear combination of product of generators. They consider these products, but we didn't see it at first. So I think that I'm talking about me, I lost too much time just thinking about this. But Dr. Maximenko tell us to work with these linear combinations. So we have this example. We finally could separate, because we learned that with just one generator, it doesn't matter how kind of symbol you put here. It doesn't matter what kind of symbol you put. You won't be able to separate just with one generator. But if we consider linear combination of products of generators, we can. Here's an example. Let n equal 2, eta equals the consecutive of C, and this matrix at well, GP is this Jacobi polynomial that we define here. This is now is GP. Is this Jacobi polynomial here? Well, but okay, here p equals 2 equals 3. Now we have for p equal 2, we will have this sequence. For p equal 3, we will have this sequence. And these numbers correspond to the diagonal of, the frequency of, well, the components correspond to the frequencies of the table of the basics, you remember? And where we have the matrix corresponding to A2 for the frequency C. You see this anti-diagonal structure, A sub 3, A3C is equal to the matrix, to the 0 matrix. A2 eta and A3 eta are these matrices, these anti-diagonal matrices. Well, let U be these two.
I'm sorry, Moisés. Do you hear me? On the previous page, what is the main idea that for Xi equal 1 for this frequency, this set of matrices is not rich enough. We have the 0 matrix, yes? And
Yes.
when we form linear combinations of products, all products will be 0. But for the frequency eta, these matrices are sufficiently rich. This is a set of generators. And from these two matrices, we can construct every 2 by 2 matrix. Yeah.
Yes, as we saw in the last result.
This is the main idea.
Thank you. Now, okay, so we already know that E3C is 0. E3 eta is just a non-zero multiple of E11. Okay, so with this matrix, this pure state is 0 because A3C is 0. And for the second pure state, sigma eta of A3 is not 0. Because as you can see here, this entry is not 0. Okay, and so and because B1 is not 0, so we could separate these two pure states. And if B0 is 0, well, we just consider G2 and G3. And consider A2 and A3. Let's denote G0, A2 eta, and G1, A3 eta. We already know that we can construct E11, E12. We can write them in terms of G1 and G0 and U1. This is E00, and this is the combination of products of G0, U1, and G1 squared. And as the matrices, since the matrices A, K, C are symmetric by the symmetric property of the matrices, we could get the transpose. Also, the transpose of E10 is E01. And if we have the transpose of the product AB is B transpose A transpose, we have this here. And by the symmetry, they are the same. And so the products always are in the algebra, and we have this now this expression for E00. Now we consider all the sequence, not just entries, not just an entry, these entries, but if we consider all this operation, this multiplication, this product of linear combination of products of G0, G1 of G's. Now we work with all the sequence. If we work with all the sequence by the same rule, we already have that the eta elements of this sequence is E00. Here. This is E00. And the key element of this sequence is the matrix 0. Here. Is a matrix 0. This is a matrix 0. So in general, we could for the different from different frequencies, we have that the pure state sigma c of x is 0, but sigma eta is not 0, because again we have this expression for the pure state. Here we have this E00 matrix is the basic matrix, and we just have B00 squared. But by hypothesis, it is not zero. So its square is not zero, so we could separate the states of these two vectors, these two pure states. So in general, we have that Xn separates the pure states with different positive frequencies in general. And I think that's all. Yes, that's all. I'm so sorry for my awful English.
It is not all. Now you say, I managed to separate all states that the algebras we are talking about coincide.
I'm sorry, I didn't get that.
Well, you finish with that you separate all states. So now you need to say final result. If you have two algebras and one of them separates all states, that by the non-commutative Kaplansky version of Stone-Weierstrass theorem, these algebras coincide. What was your idea to prove?
Yes.
This conjecture, yeah.
Yes, this conjecture. Mm-hmm.
So this conjecture is almost theorem, yeah?
So
we
it's,
still
it's already theorem.
No, we still have to separate pure states associated to
the negative frequencies.
Yeah.
Negative.
Yes, because they're just positive.
Okay.
And for positive is done. Now I need to work with negative.
What is the problem to work with negative frequencies? It's like symmetric with respect to diagonal.
I think that for negative, well, for negative, no. Well, I think for negative, we have submatrices of this. We'll have this. They will be part of this matrices. I think that
for example, Moisés, this matrix is which submatrix of?
Okay. This submatrix
Of gamma 1, yeah.
Oh, I'm sorry, gamma 1. Gamma minus 1 will be a submatrix of this gamma 1.
And what?
Well, if this happens, we can work with this integrals and just construct the matrix. No.
Well, we just have technical difficulties, yeah. We have not thought enough on all the cases because we have many cases, separate this one from this one, separate this one from this one, separate this from this one, and so on. There are many cases and a lot of technical work.
Okay. Okay, now maybe questions, suggestions, remark. Igor, maybe you start. You already did some nice remarks.
Well, thank you, Moisés, because my English is much worse.
Much better.
Much worse. And well, this work, this project is very similar to the projects by our colleagues, Armando, Josue, Maribel, Rosario, and other colleagues. but there are some differences. In this situation, for the radial Toeplitz operators on the unit disk, the matrix sequences gammas are constructed as some integrals involving Jacobi polynomials, and we have no special factor. Jacobi polynomials are just polynomials, and the weight factor, this power of t, is also a polynomial factor. So all the ingredients here, except for the same weight, all the ingredients are polynomials. And for different values of xi, they look almost the same, and they are very difficult to separate or distinguish. So in other situations, for the vertical operators on the half plane, for the homogeneous operators, there was a special factor before the integral, and this exponential factor involving the frequency or something like this. And this factor was very useful to separate.
That was the key for them to separate the states very easily.
Yeah, exactly. Separate the
In
pure
our
states.
in the radial cases, it's not, as the Dr. Maximenko says, everything's polynomial. So everything is not quite easy.
So this part of work is not gratis, is not simple, and instead of the special factor, we need to use the orthogonality of polynomials, and we notice that the generating symbol can be chosen as the Jacobi polynomial, and this gives the anti-diagonal structure. Please, once again, the example for next one. Oh, no, we have this anti-diagonal structure of the matrices, and on the page 50, maybe when we see
Oh, sorry.
This one, when we have two sequences.
Oh, we have two sequences. Here?
Next one, please. Next one.
Oh,
yeah,
okay.
This is the main idea, that due to this anti-diagonal structure, for the frequency eta, we have a rich set of generators, and for the frequency xi, one of the matrices is 0, and the products will be 0. So it will be enough to separate well, the quadratic forms associated to the linear combinations of products of these matrices are very different, and we can separate the pure states associated to different frequencies. So instead of special factors, we just use the orthogonality. And maybe this way, this method is can be convenient for other situations, because in many examples, in many situations, we have orthogonal polynomials, and we can use this orthogonality.
Well, we think that this scheme can be generalized, because all the colleagues, they also use orthogonal polynomials. So maybe this will be generalized for them, just using the orthogonality.
Okay. More remarks, suggestions, questions? Rafael, At least you should learn from this talk that there is Kaplansky non-commutative generation of the Stone-Weierstrass theorem. If the subalgebra of full algebra separate states, just they coincide.
Yes.
So it's very important result, which was used but in many papers of our colleagues to prove that subalgebra coincide with algebra.
Okay, I see.
Okay, so thank you, Moisés. Maribel, who's next?
Oh, thank you. Thank you. I'm so sorry.
Moisés, could you please stop the recording? Stop recording.
Stop. Okay.
The next speaker is Juanita.
Juanita. She will speak